All right. Hi, everyone, and welcome to this talk. Thank you for coming. My name's Ivan. I work in ESPRESSIF. ESPRESSIF is a semiconductor company, wireless chip maker, keywords ESP32, ESP8266. And basically, my talk today is actually going to be relatively remote from the IoT devices and from microcontrollers all the way until the end. And I'm going to talk about WebAssembly. So, does web in WebAssembly mean that the talk will be mostly about the web, like the internet? Kind of yes and no. So, WebAssembly was indeed conceived and designed to as a technology for the web browsers. But it has a lot of other applications, and we'll try to dive a bit into both, like web and what WebAssembly can do outside of web. So that's basically the topics we're going to try to cover. So first, I'll try to explain what is WebAssembly and what is its place in the sort of technology stack. I'll show some of the use cases to get you interested in this. Then we'll look a bit at what happens inside WebAssembly runtimes. Few words about how to create WebAssembly so that you can actually run something. Briefly about security, maybe would be interesting to someone, and I'll finish with talking about embedded WebAssembly. So first of all, what is WebAssembly actually? So there is no simple answer to this question. So WebAssembly is a few of things actually. So first of all, it is an instruction set, like for example, your Intel-based computer or AMD-based computer has certain hardware instruction set. So WebAssembly is also kind of an instruction set. But it's an instruction set not for the real computer, but for the virtual machine. And WebAssembly is kind of a specification for this virtual machine at the same time. So WebAssembly defines the instruction set and the virtual machine. And the purpose of this, one of the first purposes of this, is to let people run software written in other programming languages like C and C++ in the browser. That was the first motivation for having WebAssembly. We'll get a bit into why people even want to do that, but WebAssembly have grown beyond that, so it's not only for C and C++. In this picture I also put Rust logo there because Rust is all the hotness these days. But many other languages can also target WebAssembly. So you can think of WebAssembly as kind of like a portable execution format that can be executed in different places. It can be executed in the browser, it can be executed outside of the browser, but the thing is that it basically, because it would be hard to support running C on a web browser and C on another web browser and then Rust on the web browser. So there are lots of combinations. So by putting a WebAssembly in between, you kind of make it simpler. So let's look at some examples. So this is the first example, and it's probably an application that many of you are familiar with. It's Photoshop. But if you look at the top of the slide, you'll see something weird. It's a Photoshop in the browser. So actually, Adobe have announced maybe just a few weeks ago, in October, that Photoshop will be available as a web-based application. How did they do this? Photoshop is a gigantic application for desktops. Well, the answer is kind of complex, but very briefly, if we summarize it very briefly, it's using WebAssembly. They did it using WebAssembly. They also did it using other things, but WebAssembly was one of the key components. And as the developers put it, basically, the marketing speak set aside, WebAssembly is what allowed Photoshop developers to use their existing C++ code and run it on the web at reasonable performance. And actually, if you're interested in this, there is a nice article on web.dev about Photoshop. All right, so for the next example, which might be a bit closer to what you're familiar with, this is actually going to be a video. And what you see is it's a simulator of a RISC-V CPU. And the simulator actually runs inside the browser. But the simulator was originally written in C++, I think, using Qt. It was a simulator for MIPS architecture. Later, it was upgraded to RISC-V. And the authors are from Prague CVUT Cheveute University. So they have taken a chance that they were upgrading the simulator, and they took it to the browser. So this is a pretty complex application that has some lots of UI elements, has lots of logic. I mean, imagine emulating the behavior of the CPU pipeline. There's quite a lot going on there. And imagine now rewriting that all to JavaScript and HTML. That would be quite a lot of work, basically doing everything from scratch. Not to mention the fact that if you want to use an existing library for emulating RISC-V behavior, or for example to do disassembly of RISC-V like they do here on the left, that would be basically you need to throw out all that code and write something from scratch. So they definitely saved some effort with that. In both cases, one of the motivations for using WebAssembly, and well, as it's obvious, is code reuse. So you don't have to throw out existing C++ code. You can use it on the web as well. And it seems like it's maybe a technology which is just a crutch to get some project that is like an old project to the web browser. But it's not only that. In the case of Photoshop, for example, it wasn't even possible to rewrite the code in a way that would run at acceptable performance at the web browser, because although JavaScript interpreters, JavaScript runtimes in the web browsers, they have advanced immensely over the last decade, there is still significant limits on how fast a JavaScript runtime can be, or how fast can you execute JavaScript. So despite all the tricks that are being done by very smart people in Google and other companies, JavaScript still has some limits to its performance. So in case of Photoshop, what they actually enabled was that they could run complex image processing code at a performance that was acceptable. It's not as good as desktop performance, and I'll show a few performance comparisons later, but it was acceptable performance, like much better than that of JavaScript. All right, so those were two examples for the web. So this is, if you're interested actually in this project, there is it's available on GitHub. You can clone it and run it in your own browser. So another example which is outside of the web, and this comes from Cloudflare. So Cloudflare is an internet company, and one of the services they provide is Cloudflare Workers. So Workers is basically this kind of function as a service thing, similar to AWS Lambda, where developers are invited to execute single functions on the server side, in the cloud. So why would you want to execute single function, rather than a whole application? This is related to this trend for producing microservices. So basically, you have a very small piece of code that is very easy to understand, very easy to deploy, doesn't have much dependencies, and you compose your application from lots and lots of pieces of such microservices. And in some cases, it makes it better than a single monolithic application. Not in all cases, but a lot of applications benefit from this. So how does function as a service work? Traditionally, what would happen if, for example, let's say AWS provides Lambda and they allow you to write your application in Python. So what would they do? They would actually run a virtual machine on the server side that would have a Python interpreter in it and some libraries pre-installed. And then when the time comes to execute your function, so basically when a web request comes, they can take your Python code and execute it. Now, here's the problem. There are lots of Python versions, there are lots of Python libraries, so you kind of need to have lots of different environments. And that basically boils down to the fact that for every single customer, they need to have a separate virtual machine. Now, they probably don't want to keep all the virtual machines running at the same time, because that would be ridiculously expensive in terms of memory. So what do? Well, they kind of let the virtual machine run for some time, and then they power it down when they see that you're not getting any more requests. So there is a problem with those kind of function as a service solutions, that once you can't power up the virtual machine fast enough to reply to the incoming request. Or to translate into other terms, the first time the request comes, there is going to be a horrible delay before the function can execute. And then the cloud service can kind of speculate that if one request came, maybe the other request will come, so they have some cooldown period while they keep the virtual machine running, and it will actually respond quickly. But the whole thing is not really optimal. So All right. Like obviously you can blame this on the people who write their software in Python, and you can say, all right, let's all write our software in some language which can be compiled to native code, such as Golang or Rust or something like that. That works better, but even Golang and even Rust, they have some, or Rust applications, even if they are compiled statically, you can't put all the applications onto one server, and this is determined by the considerations of security. So it's basically for the cloud provider, every function that runs on the server is potentially a malicious function. And who knows what it does inside, even if you kind of sandbox it and limits its access to the operating system, it can do evil things. And maybe if you have like multiple customers running their code on a single VM, then their code can somehow interact, and no one wants that. So WebAssembly provides one solution for this, because what they do is effectively they create a WebAssembly runtime on the server side, and instead of loading real code, like compiled to native language or interpreted code, they load WebAssembly modules into the WebAssembly runtime. And the theory is, and we'll talk about that in a bit, is that WebAssembly runtimes actually provide some sort of isolation. So one module cannot interact with another module, and also WebAssembly by design, because it's designed for the browser, WebAssembly is very fast to load compared to some other solutions. So hopefully with that you got sufficiently excited about WebAssembly, and now you want to know how and why. All right, so first of all, let's look at the basic structure of what WebAssembly execution looks like. This is the case of the web browser, and like in the case of Cloudflare, it's going to look a bit different, but let's look at the browser case first, because it's the main one. So let's say you have an application that is written in JavaScript, and that's on the left, and you have some library that hypothetically is written in Rust or C or whatever, and it's at the top. And you want to be able to use code from the application, from that library in your application. So how do you do that? First of all, you need to compile your library as a WebAssembly module, and we'll go into a bit more detail how that happens. And then the application tells the browser to load the WebAssembly module into the runtime. The browser's runtime validates the application, and I'll explain shortly what it means to validate it. And then the application can call functions exported by the module, so it means that the module provides some function and the application can call it. That's kind of the useful functionality you want to get from the library, like decode some image format, for instance. And the module, if it needs, can call some imported functions, so functions that are defined by the application. For example, if the module needs to get the current time, for instance, you can provide a function in your application which gives the current time, and you can allow the module to call this function. So the module, most importantly, can't call just any random function in your application, or like jump to some random address in your application. It can only call the functions that you explicitly allow it to do, to call. So that's more or less what the structure looks like. And now we will look at what happens actually when the module is loaded into the runtime. So there are 4 stages, and actually not all of them are so interesting for us, but let's go through them really quickly. So there are parsing, so that's when the WebAssembly binary code is converted into some internal representation of the runtime. Then there is validation, which is a very important step, which guarantees that WebAssembly code is not malicious. Instantiation, which is basically that if you want to have multiple copies of the module, you can have them, and it's not so important. And then execution, that's where you actually call functions defined in WebAssembly. WebAssembly modules, they can be defined in text format and binary format. The text format looks like this, and if you've taken some programming language classes, you probably recognize that as S expressions. So WebAssembly text format is not usually written by hand, unlike other programming languages. It's kind of like disassembly. So if you want to look into what's happening inside a WebAssembly module that was compiled from some other language, you can convert it to the text format, and then you can look at what's going on inside. But basically, there are some tools that let you convert between text and binary formats. But the primary format in which WebAssembly runtimes take the modules is binary format. So WebAssembly, maybe a bit about WebAssembly as a virtual machine. So WebAssembly is a stack-based virtual machine. So what does it mean that it's stack-based? It means that every operation the virtual machine has takes arguments from the stack and return results to the stack. And this is not your physical stack in the machine code. This is like a virtual stack of the virtual machine. So there are different kinds of instructions. Each instruction is encoded using 1 byte. So every instruction opcode is just 1 byte. And there are, for example, arithmetic instructions, control flow instructions, load store instructions. That stuff is not very different from traditional instruction set architectures. Then WebAssembly also has interesting concepts like local and global variables. So in regular instruction set architectures, you just have memory, and the CPU doesn't care how the programmer uses the memory. So you tell the CPU, go give me that address, and the CPU will go and fetch the address from the memory and return it. Not like that in WebAssembly. WebAssembly actually takes care to designate certain types of memory. For example, local variables, global variables, and linear memory. And that is done in the name of security, because for example, on a regular computer, you theoretically, some protections being set aside, can just take a variable, for example, that you got from somewhere from the network, and you can write it into the code, basically the executable code, and then you can execute that value, which is something that viruses typically, or some evil programs typically do. Now, there are lots of protections that are built into the operating system to prevent that kind of exploitation, but still it's hard to close all the loopholes, because for a normal processor, like all the memory looks the same, regardless of how you use it. So instructions, I mentioned that there are 1 byte quantities. So you basically have, this is like a table, so the row tells you which, this is the first 4 bytes, and the column is the other 4 bytes, so every instruction can be encoded using 1 byte, and actually there are more instructions, so you don't have to know all of them. If you program for WebAssembly, that's kind of like if you program for C, you don't have to know assembly, unless things go wrong, and like here also you don't have to know this, but just there are 1 byte instructions, kind of interesting. All right, so let's say that our runtime has successfully parsed the module. It has parsed all the instructions and all those other things that I was talking about. And the next thing it does is validation. So validation is very important because, for one, WebAssembly is very limited instruction set and limited not in a bad way. So, for example, WebAssembly has structured control flow. So, like in a normal language. Most normal languages, you can't just use goto to go into any random place. And yes, see, I'm looking at you. Basically, in most languages, we somehow say that if you have like an if-else statement, then you can, from the instruction inside if, you can go outside, only outside. You can't go inside into the else. And in C, you can do this using goto, and that makes. Even if you don't specifically put a goto there is nothing actually preventing the CPU to do that. And you can trick the CPU, or, well, not you, or some evil guy can trick the CPU to do that. So that's basically the lack of structured control flow. In WebAssembly, all control flow, so all branches are structured. So there is a special branch type for if, there is special branch type for else, and the runtime actually validates that all the control flow is well structured before it allows your module to execute. So you can't trick the runtime to execute something that would not use the instruction in the way intended. And there are lots of other validations going on. For example, all instructions, they operate on specific types. For example, int32, float32, and so on. So you can't trick the runtime to treat a 32-bit int as a 32-bit float. Like you could, you can of course store it somewhere in memory and then load it and interpret it as a float variable if you really want to do that. But it's much easier it's much harder to use that for some kind of exploitation. So next, all right. So basically, let's say we got through the validation phase and we know that the module is more or less well formed. So the next step is instantiation, and I'm going to skip that because it's not so interesting. And finally, execution. So how does runtime execute WebAssembly code? And there are basically 3 types of runtimes. There are interpreters. Interpreter is basically a very simple thing. It looks at the opcode, has a huge switch statement. So you've seen that list of instructions, right? So that's approximately the switch statement that it has. It has a switch statement, and it looks up which opcode that is, and then executes that opcode, then goes back, fetches the next one, and kind of repeats in the loop. The performances you can expect is not really great, because for every single instruction you execute lots of instructions of your host CPU. But the instructions are kind of at the same level of complexity. So if you have an add instruction in WebAssembly, then actually in the CPU you execute add instruction plus a whole bunch of branch instructions to get to that add. So in terms of performance compared to native code, you're kind of losing a lot. So then there are GIT compilers, or just-in-time compilers. So what is a just-in-time compiler? Basically, it's a thing that looks at the code like at the function level or at the block level, and when necessary, it will try to compile it to the native code and then execute it as native code. And ahead of time compiler is basically the same thing, but it does it for the whole program before the program is even executed. There are some differences in terms of performance you can get from JIT and AOT, but in the interest of time, I'm not going to get into that. If anyone has questions about that, and I can answer afterwards. So to get an idea what kind of performance you can expect, this is a benchmark table that was this benchmark table was prepared by the author of Wasm 3 runtime. That's number 4 from the top. So all the core mark. So core mark is one of the benchmarks. It's basically like CPU and memory benchmark. And the higher core mark score is better. So the relative scores, they are normalized to Wasm 3 score. So you can see that, for example, native is admittedly a lot better than any WebAssembly interpreter. But some WebAssembly interpreters are getting pretty close to native. So for example, with this WAVM, you can get like really, really close to native performance. And everything like Wasm 3 and everything that is less performant are interpreters. Everything between Wasm 3 and native, those are some kind of just-in-time or a combination of just-in-time and ahead-of-time compilers.
I would like to ask whether these interpreters are directly interpreting the C code or some pre-compiled or compiled code?
They are directly executing the WebAssembly code. So they are taking the opcode, like that 1-byte opcode that encodes some instruction, and then they look what opcode this is, and then they do something about it. So Wasm 3 actually is a bit smarter than that. It doesn't use a switch statement. It has like a tail call based. It's a tail call based interpreter, which is a pretty interesting thing. So that's why its performance is a bit higher on some systems. Okay, so I need to speed up a bit. Creating WebAssembly. For C, C++, mscripting SDK is the go-to. It basically is based on LLVM compiler. Rust has a target for WebAssembly, and for other languages there are some solutions as well. At the moment, if you have a dynamic language, then WebAssembly is not a very good target, because WebAssembly doesn't allow for the kind of things that dynamic languages tend to do. So if you have a dynamic language, then what you can do at the moment is you can get the interpreter for that dynamic language and compile that interpreter using WebAssembly. So you will effectively have a dynamic language executing inside the interpreter, or inside the runtime, kind of inception. And people even have executed WebAssembly interpreters inside other WebAssembly interpreters, just for fun. So, all right, I'm going to skip this one and go to security. So, one of the reasons why WebAssembly is interesting is because it provides that sandboxing that I talked about, and it is achieved through a number of means. Some of them I already mentioned, like structured control flows, go-tos, but also there is strict isolation between types of memory. So basically the program never has access to the stack, which it does have on a real system. The program never has access to just random location memory, so it's always just the memory that you give to the program. And this actually makes WebAssembly pretty interesting in terms of sandboxing. Of course, there are bugs, like exploitable bugs in interpreters, but there are not too many of them. If you search, for example, the CVE database for Wasm, then you will basically find about 23 CVEs to date. And if you search for CVEs in Google Chrome alone, then you will probably find like around 100, only in a couple of years. So there is a lot to be said about using WebAssembly if you want to provide some sandbox, some isolation. You want to run the code you don't trust. And finally, getting to why I think WebAssembly is interesting and why I am talking about why WebAssembly is interesting is WebAssembly outside of the browsers and specifically on embedded hardware. So although it kind of is weird that you take such a resource-constrained device and you try to run something as complex as an interpreter, it actually makes sense in some ways because, for instance, what we can do is we can run some logic on the IoT device, and we can load this logic dynamically. So think of, for example, your smart thermostat that has some rules, like you want it to follow, for instance, some time, or you want to follow some like temperature measurement from some device. Currently, this logic is implemented on the cloud side, and if your internet is down, then the thermostat will not work. So what WebAssembly does allow us to do is to compile this logic on the cloud side, and we can execute it on the cloud side using WebAssembly. But if internet is down, we can execute the exact same WebAssembly logic on the embedded device. And this, I think, flexibility will be used quite a lot in the coming years as embedded devices become more powerful. So with that, thank you. And if anyone has questions, I will answer them.
I still didn't understand where is it compiled, on which side, whether on the server side or on the client side, and what are you transferring over network?
Yeah, so basically you take for example C code, you compile it on the server side using CLang or LLVM, you get a WebAssembly file. And that WebAssembly file can be again executed on server side using some server targeting runtime. It can be executed in the browser if you want to build some kind of simulator. And you can also load it to the device and execute it on the device.
And it's like the interpreter universal for all the browsers?
The implementation is different, but the WebAssembly module, once you compile it, will work in all the browsers. And if it works in the browser, it will also work provided that you give it enough memory, it will also work on the embedded device.